wonder why every few years we add an extra second to our clocks? It's called a leap second, and it all comes down to Earth's changing rate of spin. Put on your thinking caps, folks, because we'd like to welcome back CMC Physics and Astronomy Professor Dr. Joe Carson, here to help us understand what this means to our everyday lives. And Dr. Carson, I mean, it sounds trivial, a second every several years, but it actually does have an impact.
It does. You might not think about it like, okay, well, if the day is slightly shorter, slightly longer by, a second or fraction of a second, what does it matter? But time is actually very heavily embedded in our technology, particularly things like satellites or telecommunications. They rely on very, very precise measurements of time. Anything like, especially things like GPS, or if you're using Google Maps that you want it to work, they need really precise measurements of that. And so anytime you have an error in that clock, or you have clocks that are on different times, it can actually lead to a lot of problems, which is why they add in this leap second to do this kind of correction every so often.
Interesting. And I was also wondering how one could be so very precise about the time. I mean, I've got a lot of clocks in my house. One's a minute off here, there, my watch is not exactly perfect, but where are we tracking the time in its absolute perfection? Where is it in the world? How is it being done?
Yeah, there's a couple different ways to do it. So one is just knowing how much time has passed, and then the other one is actually seeing the length of the day, like how fast Earth has actually spun. So knowing how much time has passed, the most accurate way to do that is with something we call atomic clocks. We're actually looking down at basically at the subatomic level, and we're seeing vibrations of atoms, and they're so precise that so many vibrations get ticked off for a given amount of time. And so there's those measurements there, and then the other side of that is having super accurate measurements of the length of a day. Because a day, right, is 24 hours, but actually, the reason why the leap second is there is sometimes it's slightly longer and sometimes it's slightly shorter. And a main way that they do that is actually by actually doing astronomical observations. You can compare Earth's position, its pointing position compared to the stars. In many ways, it's similar to what, like in Charleston, what ancient navigators would have done when they would have used the stars to track both their position as well as the local time. We actually go back to that again to have the precise measurements of Earth's spin rate.
Right. I mean, for the longest time, people have been able to track the time pretty accurately before watches or clocks were really a thing. I mean, people were using sundials and, measuring the sun that way, which I guess is a little less scientific. But that's really interesting. So how were they able to do that back in the day? They would measure the passage of time by celestial objects, by stars, by the sun, the moon. The most difficult part of that, which is why navigators were such experts, is when you're changing time zones. And then all of a sudden you have that effect because the sun is rising earlier or it's setting later. So they had to track that as well. And you can actually use that information to figure out how far east or west you are. And for doing that, they would take very accurate measurements of when the sun rose, when the sun set, or they would look at also the rising and setting of constellations in the sky. And they would look at how those changed, and they could tell when their time zone was changing. So are any of those old techniques still used today for any reason? Is there no reason to? Have things just become so advanced?
There's, for example, like for some things, things like cruise missiles, for example, just to give one example, that have very, very, very precise positioning. They can't use objects on the ground to see where they are because sometimes the ground, if you're over the ocean or you're over desert, the most accurate way to for things like either missiles or rockets to find where they are is actually to use the stars. So it sort of seems odd, but actually historically things like cruise missiles have taken active observations of the sky as they travel to figure out exactly where they are and where they need to be.
Interesting. Based off of how the leap seconds work, historically speaking, does it seem that the Earth has a pretty structured way in which it rotates and moves and spins? If you were to compare it 10 years ago, 30 years ago, 70 years ago?
So your spin
or is it changing at all? It is changing. It's almost perfectly constant, which is why these changes are very small. We talk about a second or a fraction of a second. But there are these small fluctuations that change how fast the Earth spins. It's not just one thing. It's due to a combination of factors. So one of them, for example, is the gravitational pull of the moon. When the moon is slightly closer, slightly further away from Earth, that has an effect on the spin rate. And another part of it is climate change. So when you melt the polar ice caps, you redistribute the mass of Earth. So all of a sudden, Earth starts to get sort of a heavier midsection. You know, a little bit like Thanksgiving dinner.
Yeah.
So you get and that heavier midsection impacts how it spins. The same way, if a figure skater, you know, gains weight or loses weight, that's going to change how fast or how slowly they spin.
Right.
And so those combinations together can cause fluctuations in the spin rate that can be much larger in 1 year or 1 decade than a previous year.
So fascinating. Thank you so much for explaining it to me like I'm a 5-year-old, because this is the only way I can truly understand it, because you've made it so accessible to the layperson to really understand how our Earth works, and that's very important. Thank you.
Thank you.
We'll be back after this.